এটা লাইভ হচ্ছে।
আচ্ছা, লাইভ শুরু হয়ে যাবে?
হ্যাঁ, শুরু হয়েছে।
Good afternoon, everyone. As a convener of this webinar, I, Dr. Shubhankar Saha, welcome you all to this YouTube live streaming platform. I hope all of you are safe and doing well. I want to thank everyone who has registered in this webinar and encouraged us to create such an exciting event where people are meeting for their interest and love for mathematics. We are pleased to announce that we have received overwhelming responses from different parts of India and abroad. Without wasting time, let's move on to the main program. The program is scheduled to be happen in the following way. At first, our respected principal sir, Dr. Manishankar Roy, will deliver a presidential speech, followed by a special address by our IQAC coordinator, Dr. Shinjini Basu. After that, Dr. Kanti Chakraborty, HOD and joint convener of this webinar, will introduce our speakers, and finally, we will move on to the lecture session. But unfortunately, our principal sir is absent due to some essential academic and administrative works. So on behalf of him, I am reading the message sent by him. Good afternoon, everyone. I am happy that after the successful completion of the webinar on 30th June, the Department of Mathematics, in collaboration with IQAC, could arrange another web meet today. This time, they have focused in purely mathematical topics. They have restricted the participation among the people from science and engineering backgrounds. Still, they have huge responses from nearly 400 institutions in India and a few from outside of the country. Firstly, I would thank the convener, Dr. Shubhankar Saha, for convening such an event. My thanks are extended to Dr. Shinjini Basu, IQAC coordinator, and Dr. Kanti Chakraborty, head of the Department of Mathematics, for their involvement and support. I must thank all attendees for participating in this webmeet. I know that the subject mathematics demands a board and chalk teaching for understanding the rigorous concepts. In the current situation, there is no way out for classroom. But on the other hand, learning process should not stop also. I personally believe that in the lockdown and post-lockdown periods, in the this type of arrangements will be inevitable in teaching and learning process. We shall experience a huge paradigm shift in the arena of education system. Today, we have two young, enthusiastic professors come researchers in our session, Dr. Timir Karmakar from NIT Meghalaya and Dr. Pavel Pal from Bankura University. I welcome them. Our students community will not only acquire knowledge from their talks, but also will get motivation from them in mathematical researches. I am very sorry that I could not attend the program due to some workloads. Though I wish all the best from today's program, I will look forward to the happening of some more events from my institution in near future. Thank you all. Now I would request our IQAC coordinator, Dr. Shinjini Basu, to say something on her part.
Thank you, Shubhankar. Good afternoon to everyone present. The respected head of the department of mathematics, Dr. Shubhankar Chakraborty, and the convener of the web, Dr. Bankura Saha, the persons, everyone, all the participants who have joined us today. Today's web meet is part of a series of such interactions that the Department of Mathematics has been organizing over a period of extensively organizing over this lockdown period. And each and every one of such engagements have been extremely successful and enlightening. Today we have two young scholars, researchers, and dedicated teachers among us. Dr. Timir Karmakar, Assistant Professor, Department of Mathematics, National Institute of Technology, Meghalaya, and Dr. Pavel Pal, Assistant Professor, Department of Mathematics, Bankura University. Again, like our principal sir, I also welcome them, and I hope that today's would be a very, very fruitful, engaging, enlightening, and enjoyable session for everyone present. Thank you.
Now I would request to our head of the department to introduce our speakers, Dr. Kanti Chakraborty.
Thank you, Shubhankar. Let us move to our main session. First, Dr. Timir Karmakar will deliver his talk. After that, we will have a question answer session, and then we'll move to Dr. Pavel Pal's part, and we'll have question answer session. This is our provisional schedule. So first, I would introduce Dr. Timir Karmakar. He is currently affiliated as an assistant professor, Department of Mathematics in NIT Meghalaya, National Institute of Technology, Meghalaya. He did his PhD from IIT Kharagpur in Mathematics Department. His area of research includes flow through porous media, fluid mechanics, PDE theory and its application, heat and mass transfer. He has published some invaluable research works in the reputed journals like JFM, Journal of Fluid Mathematics, Proceedings of the Royal Society, and others. He has presented his works in several conferences in USA and Canada. He is a life member of Indian Mathematical Society, Indian Society of Theoretical and Applied Mechanics. Besides being a finest researcher in the current time, he is very supportive teacher and good human being. Moreover, he is very much down to earth and always prefers to meet the students of his home state, that is West Bengal. Let us enlighten us to his talk. Please, Dr. Karmakar.
Thank you very much, Dr. Kanti Chakraborty, for such a nice introduction. And so, as Dr. Chakraborty requested me that to make this talk that will be only confined to some UG and PG students. So, my talk actually I'll talk about some basic themes about PD and some of its application. So coming to the talk, yeah. So is it visible to everyone? Yeah. So as you can see, the title of my talk is Elementary Solution Method for PD and its application. So this is the outline of my talk. So first I'll talk about some basic things about PD, and then some its application. Okay. So when you when we talk about PD, so first question comes to our mind that what are PDs? So to know the PDs, we have to go a little bit back up. So first, let us recall what is an ODE. So ODE is actually, it is a equation of this form. So here you can see that X is the independent variable and Y is the dependent variable. So here only one independent variable is there. So an equation of this form is the ordinary differential equation. Now, when we have more than one independent variable, so suppose we have two variables, right? So then we cannot express the phenomena, whatever the process in terms of ODE. So then we have to describe by PD. So suppose this is two independent variable is there, then the PD is of this form. Okay, so here you can see ux and uy. So this depends on the actually the variable ux, uy. So in terms of geometry, if we think, so these are the nothing but the directional derivative, right? So ux means it can be considered as the directional derivative in the x direction. Similarly, uy. So PD is the more generalized thing. Okay. So now, why this PD are useful actually? So in several real life phenomena, if we see, those depends on time, space. In fact, if we consider any real life phenomena in 3 dimensions, there also we have 3 variables. So we have to rely on PD. So I am giving one example. So suppose if we drop a ice into a glass of water, so there you can see that after some time the ice will melt into the water. So what is this phenomena? So this is nothing but a heat transfer phenomena. So after some time it will melt down. That means the phenomena, that is the transfer of heat, actually depends on time and space. So after some time, when it will totally melt down, that means it will reach an equilibrium. So this will totally become liquid. So this says actually this is this can be described by heat equation. Okay, so later on we will learn that heat equation is also a PD. Okay, so similarly, if we drop a stone into a pond of water, then where we drop the stone, so from there we can see that the wave of this kind of thing form. So spherical waves come from a point source. Point source means where we put the stone. So this is also nothing but the 2-dimensional wave equation. In spherical coordinate we describe, this is called the spherical wave. So this is nothing but a wave equation. So wave equation also later on we will learn that this is also a PD. So later on means we'll discuss that this heat equation is parabolic type and this wave equation is hyperbolic type. In fact, apart from these 2 phenomena also, there are several phenomena in real life. Actually, in fact, the natural law of physics and Newton's law of motion, heat and mass transfer, in several phenomena, these PDs are very useful. So now, what kind of PD? So actually, before going to the classification of different kind of PD, first let us get some idea about what is the order of a partial derivative. So it is nothing but, as we know the definition, that it is the highest order partial derivative, same as ordinary differential equation. So the definition. So if it is like this highest order partial derivative is xx, that means it is second order. So similarly, this is third order, right? So now classification of PD. So once we have the order of a PD, we can classify the PD. So if it is a first order PD, so we can classify of this type. So please follow the notation P equal to this del z by del x and Q equal to del z by del y, where z is the dependent variable and x and y are the independent variable. So if a PD, of course, first order PD, if it is of this form, where this means xy and qxy, that means p plus q equal to r xy into z. That means z into some function of xy, then we call it as a linear PD, right? But if the left hand side is of this form, but right hand side we cannot explicitly written z into r of xy, then we call it almost linear. When it's become z into some function of xy, then we call it is a linear, right? And quasi-linear is a more generalized form. It actually consider these two, means both linear and semi-linear. So quasi-linear PD of this is of this form, PP plus QQ equal to R. So it can be dependent on dependent variable, independent variable, both, right? And if a PD, first order PD, not of any of this form, this above 3, then we call it is a nonlinear PD, right? So this is the classification of first order PD. Now coming to the second order PD, of course, second order linear PD. So suppose it is a U is a dependent variable and it is a function of independent variable x and y. Okay. So if it is a second order PD of 2 variables, then what will be the general form? So we can write it in this form, right? So now we can see that this form has some sort of resemblance to the quadratic form, right? Ax square plus bxy cy square. So that kind of thing, quadratic. So accordingly, due to that resemblance, this terminology came. So parabolic, if this b square minus 4ac equal to 0, then we call it as a parabolic PD. If b square minus 4ac greater than 0, then we call it as a hyperbolic PD. And less than 0, then we call it as elliptic PD. So these are some examples. So this is actually that ice melting process. What we have just shown a video. So this is the ice melting process. This is nothing but the heat equation. Okay. Similarly, this is the wave equation, right? So that throwing a stone into a pond. So that is the wave equation. So this is the hyperbolic equation, right? So now, suppose it has more than 2 independent variables, or rather, let's say it has n independent variable, right? So suppose U is a function of x1, x2, xn. So if it is a second order PD of n independent variable, then what will be the general form? It will be of this form, right? Now we cannot classify this like b square minus 4ac form, right? When it is a general form, then we will get a corresponding matrix, Aij. Now this Aij will tell us what kind of PD is this. So if one of the eigenvalue is 0 and all others are same sign, then we call it as a parabolic PD. If none of the eigenvalues is 0 and one of them has opposite sign of the n minus others, that means n minus others hyperbolic PD. And if all the eigenvalues are of same sign, positive or negative, we call it as a elliptic PD. So let us give some example. Suppose this ut equal to this. So here if we see the corresponding coefficient matrix will be of this form. Now you can see this is a diagonal matrix, right? So eigenvalues will be the diagonal. So eigenvalues are 1, 1, 0. So one eigenvalue is 0. That means it is a parabolic PD. So similarly here, one eigenvalue negative and rest are positive. So this is a hyperbolic. Here we can say that all eigenvalue is of same sign. That means positive. So this is elliptic PD. Now coming to the solution. So before coming to the solution, we need to know these two definitions of PD. So first, what is general integral, or some time we refer to as general solution. So if the solution contains as many as arbitrary function as the order of the PD, that means the solution involves the arbitrary function. And how many arbitrary function is there? It has as many as the order of the PD. So suppose it is a second order PD, so it will have, if it will have means 2 arbitrary function, then we call it as a general integral. Okay. So it is if it is a third order PD, then we will have 3 arbitrary function. So that is the general integral. So general integral involves arbitrary function. Now coming to the complete integral. So complete integral will have arbitrary constant. Okay. So how many arbitrary constant is there? So number of independent variables. Okay. So suppose it is a second order PD of two independent variables x and y, then the solution will be actually function of x, y, z. And how many constant will be there? Since it has two independent variables, so f of x, y, z, a and b. So two arbitrary constants will be there. So that is the complete integral. So coming to the solution of first order PD, so we can quickly look at this chart. Here we can see that first order PDs we have already classified that it has of this form. So quasi-linear, so that is the general form that covers linear, semi-linear both. So let us say this quasi-linear and non-linear. So now if this is the quasi-linear, so then we know that we can apply this Lagrange's method. So the method is nothing but that we have to write the Lagrange's auxiliary equation and then solve. And if it is a non-linear PD, then we can apply this Chakraborty method. So Chakraborty method, so what is the means Chakraborty method we can apply for only two independent variables. Okay. Now suppose we have a first order PD, non-linear PD, let us say, more than two independent variables, right? Then we cannot apply the Chakraborty method. Then one generalized method is there. So that is called Jacobi method. Okay. So I guess in basic PD course you have learned this Lagrange's method and Chakraborty method, but this Jacobi method is more generalized. So here I will talk a little bit about this Jacobi's method because these two methods you have already learned. Let us talk about Jacobi method. Jacobi method, actually the basic idea behind Jacobi's method is the compatibility of PDs. So when we say that two PDs are compatible, so let us say f and g. So f equal to 0 and g equal to 0 are two PDs. So to compatibility means they will share a common solution. Okay. But it doesn't mean that every solution of A will be a solution of G. But if this F and G are compatible, they will have at least a common solution. Okay. So which will help us. Suppose we want to find the solution of F. So you will not directly find the solution of F, rather we'll find a solution of G which is compatible with F, right? And the common solution. So that common solution will actually by default will be solution of F. So that is the idea. Okay. So suppose this is the system. Okay. Or rather this is the PD. Okay. So X, Y, Z. So three independent variable is there. So since it has three independent variables, we cannot apply this Chakraborty method, right? So that's why we are actually talking about this Jacobi method. So to solve F, what we will do? So we will find one parameter of family like H1 and H2, so that this H1 and H2 are compatible with F. So both are compatible with F. Then once this is compatible with F, these two PDs, then we will find this condition. So after integrating this, okay, we'll get the U. Okay. So now how to find this Ux, Uy, and Uz, right? So that once we have this, we will just simply integrate this. Okay. So now how to find Ux, Uy, and Uz, and also which assures that this will be integrable, right? So for that one theorem is there. So if H1 equal to 0 and H2 equal to 0, these two PDs are compatible with F equal to 0, then it will satisfy this relation. Okay. So if we write this relation explicitly, so we'll get this thing. This is nothing but Jacobian, right? If we split this, we'll get this. Okay. So now, if we see, this equation is nothing but, what kind of equation is this? This is some sort of quasi-linear PD, right? So like PP plus QQ equal to R. Okay, so there is two independent variables. So suppose it has also this quasi-linear equation more than two independent variables. Okay, so for that, for Lagrange's equation, what was the corresponding auxiliary equation? Dx by P equal to dy by Q equal to dz by R. But since it has more than the two variables, so some sort of similar auxiliary equation we can apply. So dx by, instead of P, there will be dx by Fux, similarly dy by Fuy, dz by Fuz, and also this rest of the term. So this is called the Jacobi's auxiliary equation. So once we have this equation, from there we can find this Ux, Uy, and once we have Ux, Uy, we can substitute the main equation and obtain Uz. Once we have Ux, Uy, Uz, we will just substitute this equation and we will get the U. Now this U is the actually common solution that will be the solution of F, H1 and H2. Okay, so that is the actually interesting thing about compatibility. So let us give an example. So here I will give an example. So suppose we have this kind of PD, f of x, y, z, pq. That means while z is the dependent variable, x and y are the independent variable. So we can apply, this is system we can apply for this particular PD. Since it has two independent variables, we can apply Charpit method. Okay, but with Charpit method, you know, so here we'll discuss that how we can get the same solution. What we can obtain from Charpit method from Jacobi's method, right? Because Jacobi's method we can apply for this system also. This is the more generalized form. Okay, so what is the idea behind it? So we have to make it of this form, right? Because Jacobi method needs this kind of form, x, y, z. That means more than two independent variables. Then only we can write the Jacobi's auxiliary equation. So that means we have to reduce or transfer this equation into this form. So what is the idea behind this? Suppose this is the Ux, y, z equal to C is the solution. Then if we derivative with partially with respect to x, we can obtain zx, that is P. Similarly Q. So once we have P and Q, we will substitute in this equation. So once we substitute in this equation, we will get the reduced PD of this form. And once it is of this form, we can apply this Jacobi's method, right? So let us give an example. So find the complete integral of this PD. Now this is, if we apply Charpit method, we can, this is straightforward, you can apply. You already know this. Now let us discuss how to solve the same PD by Jacobi's method, right? So what is the idea? So P we have to substitute what we have discussed, that minus Ux by Uz. Similarly Q. So once we substitute P and Q in the main equation, so we will get a reduced PD of this form, right? So now you can see that this is of the form G of x, y, z, ux, y, uz, where x, y, z are the independent variable, u is the dependent variable. Now it is actually ready to apply Jacobi method. So once we apply this Jacobi method, we will get this auxiliary equation. So after solving this, we'll get ux and uy. So once we have ux, uy, we'll substitute in the main equation. So we'll get uz, right? So now we have uz. So that means we have to substitute ux, uy, uz into this equation. So once we integrate, we'll get this equation, right? So this is the solution. Now, what is the aim of our? Our aim is not to find u, Rather, our aim is to find Z, right? So now, and also, this is how many independent variables is there? X and Y. That means the complete integral will involve how many constant? Number of the independent variables. That means complete integral will have 2 constants. But you can see here it has 3 constant, arbitrary constant, right? A and B and C. So how to choose the third constant? Okay, so this is the C is the third arbitrary constant. So we have to choose U equal to this C as the solution, this same arbitrary constant. So once we choose U equal to C is the same arbitrary constant, then you will get cancelled. So we will get this complete integral. So that is our final aim, right? So that is the final thing. That was our aim, to find Z in terms of 2 arbitrary constant. So this we have found by Jacobi's method. You can check, you will get the same solution if you apply Chapter method. So that is the first order PD. Okay. Now coming to the second order or higher order PD. So there is an entire arsenal of methods to solve this second order PDs, but most important methods are actually those that changes PD into ODs. Okay, and those are very useful and also is less complicated. So here I am giving a flowchart. So PD, of course, this is we are talking about second order or higher order PD. So PD, suppose it is a linear configuration, then suppose it is of regular domain, then we can apply this separation of variable, integral transform, and eigenfunction expansion method. Suppose the PD is linear, but the domain where it is defined that is irregular or some nonlinearity is there, then we have to rely on some semi-analytical method. Also perturbation method is there, and also we have numerical method like finite difference method, finite element, and also several numerical methods are there. So here the configuration is nonlinear. Now suppose the PD is itself nonlinear, right? That means nonlinear term is there in the PD. So there also we have to rely on some approximate solution such as perturbation method, similarity transformation, and numerical solution. So in the coming slides, we will discuss a little bit about the separation of variable, one linear configuration, and one perturbation method, one nonlinear configuration. Then we will discuss some application. Okay. So coming to the separation of variable. So when we can apply actually this separation of variables? We cannot apply to every PD. So if the PD is linear and homogeneous, okay. So linear means it will have a trivial solution, and homogeneous means it will have, and linear, you know, the linear, not necessarily constant coefficient. That means it can have a variable coefficient also. But the main thing is the boundary condition should be this kind of thing, homogeneous, okay, and initial condition are non-homogeneous. Then the idea is we'll separate from the terminology. You can see the separation of variables means separation of actually independent variable. So how many independent variable is there? So accordingly we'll separate and we'll find the corresponding ODs after separating. Then we'll apply the Fourier series method, or actually we'll find the constants, arbitrary constant based on the boundary and initial condition. Okay. So let us give an example. Okay. Suppose this is the PD, this is the boundary condition, this is the initial condition. So you can see that the PD is linear, homogeneous. Homogeneous means U equal to 0 will be a solution of this PD, and boundary condition is homogeneous. So how to solve by separation of variable? So seek a solution of this form. So how many independent variable is there? 2 independent variables, T and X. So accordingly we separate XX into T and T. And once we substitute in the main PD, so we'll get this kind of thing. Okay. So you can see the left-hand side is a function of t and right-hand side is a function of x. So when these two functions will be equal, arbitrary function, these are a function of t, function of x, and these are equal means they are equal to a constant. So we call k is the separation constant. Okay. So now, once we will have these two PD, two OD. So idea is that. So now PD is actually reduced to 2 OD. So now, how to choose this separation constant? So who will tell us about the separation constant? So boundary condition will tell us. So in this case, we will choose the separation constant to be negative because we want a steady solution, that means independent of t as t tends to infinity. We can actually think in physical sense also, like when we are putting an ice, so after some time it will melt, right? That means after some time means, let's say some large time, it will totally melt down. That means no heat transfer will happen. It will be totally steady kind of thing, right? So that we have to choose this k equal to minus lambda square, so that e to the power minus t kind of thing will come, minus lambda square t, so that as t tends to infinity, it will independent of t. So once we have these two ODs, so we can find the solution. Okay, so once we have the solution, we will apply the boundary condition and initial condition. Okay, so when we apply the boundary condition, so we will get a eigenvalue problem, rather a strongly value problem, you can say. So once we apply the boundary condition, we will have sin lambda equal to 0. That means lambda equal to n pi. So this n pi, this is called the eigenvalue, and correspondingly sin n pi x. So this is called the eigenfunction. So now, what is the building block? Actually, that means corresponding to each n, un will be a solution of a PD, right? That means this part is the t and t, this part is the x and x. So once we have, now we have already done with the boundary condition. Now one condition left, so that is the initial condition, which will give us this constant an, right? So now, once we apply the initial condition, so we will get this kind of thing. Okay. So now, why actually the linear PD is required actually? Why we talk about the linear PD? So this is the main thing. So since it is a linear, we can take that since it is a linear PD and each un is the solution of PD, their infinite sum will be the solution. Infinite sum will also be the solution. So linearity gives only this. So this is called the superposition principle. Okay. So now once we impose the initial condition, we will get this kind of thing. Now this an we can find by, because phi x is known, so an we can find by that Fourier series expansion, right? So this is the separation of variable for homogeneous PD. Now suppose we do not have homogeneous boundary condition. Okay, we have non-homogeneous boundary condition. So G1T and G2T, these are the non-homogeneous term, right? So now we cannot apply separation of variable until we reduce to this homogeneous, non-homogeneous boundary condition to homogeneous one. So how can we transfer this non-homogeneous boundary condition to this homogeneous one, right? So I am giving an example. So suppose this is the PD and this is the boundary condition. So here clearly we can see this non-homogeneity is this K1 and K2. So we cannot apply directly separation of variable, right? So we'll split this into two forms, uxt plus fx, where uxt in physical sense we call it as a transient or unsteady. That means depending on t, and fx is steady, that is independent of t. So once we substitute this into the main equation, what will get? This kind of thing. Similarly, boundary condition, you get this kind of thing. So now you can clearly see that how to choose this f. So you want homogeneous boundary condition and homogeneous PD. That means we have to choose this equal to 0 and f of 0 equal to k1, f of l equal to k2. So once we choose this, we'll get the homogeneous PD along with homogeneous boundary condition, right? So once we choose, we can solve fx as this. So now what will be the new initial condition? This will be phi x minus fx. So let us say this is the new phi x. So now our reduced PD is of this form. Now we know how to solve. We'll apply just separation of variable. So now we had non-homogeneous boundary condition, but we reduced to a homogeneous PD and then solve. So this is the idea. Okay. So here we discussed about how to actually deal with the non-homogeneous boundary condition. Now let us say we have non-homogeneity in the PD itself, not in the boundary condition, but in the PD itself, right? So this is the PD and non-homogeneity is this term, f of xt. So how to deal with that? There also we cannot apply separation of variable directly. So in this case, the idea is some sort of separation technique, but that the second variable, one variable will take, or rather the eigen function will take from the associated homogeneous equation, and the other will substitute in this equation and then solve. So that technique is called the eigenfunction expansion method. So let us give an example. Okay. So suppose this is the PD. So now non-homogeneity term is coming because of this. Okay. Boundary condition is homogeneous, initial condition is non-homogeneous. So this is the problematic, right? This creates problem. Okay. So how to deal with that? So we'll assume of this form. This is also a separable form, you know. But this sin n pi x actually is nothing but the eigenfunction of the associated homogeneous problem. Right? Similarly, sin 3 pi x also we split like this. So once we substitute in the main equation, we'll get this kind of thing. And FNT we can get using the orthogonality of eigenfunction, sin m pi x into sin n pi x when m equal to n. It will give half, otherwise 0. So you know this is the orthogonality eigenfunction. Using this, we'll get this solution. So this is a little bit complicated, right? When we have non-homogeneity in the PD. So now there are more easier way to solve this, to deal with this non-homogeneous PD. So that is the superposition principle. So that is the actually backbone of any linear system, either linear algebra or any differential equation or PD, any linear operator, LU equal to F, then we can apply this superposition principle. What it does, so it actually break into elementary parts. So that elementary parts will give you easier situation to solve. So once you solve, again you sum. So this is the solution. Suppose we have a LU equal to F. So non-homogeneity is coming because of F. What you will do? We'll split into this form. So corresponding to each K, each Fk, we will have LU K equal to Fk. So corresponding to each Fk, we have UK. Okay. So after finding U1, U2, UK, what we will do? We'll just add. Okay. So then this addition will be the solution. So that is called the superposition principle. Now please note that we can apply this only for linear operator. That means L should be a linear operator. Okay. So I am giving an example. Suppose consider an ODE. Okay. To know what is actually superposition principle is. So consider OD of this form, right? So how many non-homogeneity we have? We have 3 non-homogeneity. 1 in the PD itself and 2 in the boundary condition. So that means we can split into 3 OD, Y1, Y2, Y3. So how many parts we can split? The number of non-homogeneity. So since it has a 3 non-homogeneity, we can split into 3 OD. Taking one non-homogeneity at a time, we have to solve the system. And rest is homogeneous. So first, this is the non-homogeneity. Taking one non-homogeneity, rest homogeneous. Similarly, second, this is the non-homogeneity, rest homogeneous. Third, this is the. Now we have Y1, Y2, Y3. Then we add the solution. Right? So this is the solution. So you can see if we want to solve this together. So for OD, you can see this is easier, but for complicated thing, suppose PD, this is difficult. But the superposition, if we apply the superposition principle, then we can split into simpler OD, then we can solve. So this idea will apply, we can apply for PD also. Suppose this is the PD, so this is the non-homogeneity. So how many non-homogeneity is there? One in the PD itself, one in the initial condition. So as we discussed, we can solve this problem by eigenfunction expansion method, but that will, as we have seen, that is a little bit complicated. So what we can do, we can split into simpler PD. So since it has 2 non-homogeneity, we can split into 2 PD. So taking one non-homogeneity at a time. So for the first PD, let us take this as the non-homogeneity, rest homogeneous. For second PD, this is the non-homogeneous, rest homogeneous. So what will be the final solution? This U equal to U1 plus U2. Okay. So till now we have discussed the solution technique of the PD. Now where we can apply this solution into real life problem. So one of the problem is lifting a large object from an anisotropic porous bed. So please do not confuse with the term. So let us discuss about what is the problem actually. So suppose we want to lift an object, large object, which is inside the seabed, and we want to lift. For example, suppose we want to lift a salvage a sunken ships, okay, or we want to find that how much force is required to lift the object up, or rather complete the process, total detachment from the seabed. This is also application in submarine technology. Suppose a submarine is at a rest, then means how much time or how much force it requires to detach itself from the bed. Okay, so that will depend on the soil and rest of the thing, means the force. So this complete detachment process, okay, that means it has submerged in the seabed. Now we want to lift the object up from the seabed. Okay, so that complete detachment process is called the breakout phenomenon. Okay, means when we detach itself completely from the porous bed, that means we can say that a breakout has occurred. Okay, so now means why you studied this problem. So this will help us to give a priori estimate about the time constraint, means how many force is required, how much force is required, how many means security personnel is required. Okay, so depending on that, we can get a priori estimate and correspondingly we arrange. So the problem is some sort of this. Suppose this is the seabed and this is the object. We want to lift it up. So let us say for the timing, this object is this kind of cubic kind of thing. It is a linear configuration. And we want to lift the object up from this porous bed. Now coming to the anisotropy and porous. So porous means you can see, means you can think as a soil. So porous, actually this terminology come from the, you can see that soil or sand, it has some pores. So whenever we talk about the flow through this soil, that means flow seeping through that pore. Actually, so soil is a porous bed, or rather here in this particular configuration, the sea bed is a porous bed. And anisotropy means, aniso means actually direction dependent. So it may be any property. So suppose you want to, let us give an example. Suppose you want to cut a wood along its grain, it is much easier than to cut it opposite to its grain. So wood can be think as a anisotropic media. But for anisotropic porous media, which property depends on the direction? That seeping rate. So means there is one term that is called permeability. So that will gives us how much it will seep. So that permeability, if the permeability depends on the direction, so we call it as a anisotropic porous media. So seabed is also some kind of anisotropic porous media. If you see the seashore, if you lift a soil, means some soil, then you can see that in the above there is sand, means sandy kind of layer is there. But after that, some black silt or clay kind of is there. So that means the actually bed is formed stratified. So the permeability will not same. So it will, since it is means different for different kind of soil. So if we configure the total soil, so it can be considered as a anisotropic porous media. Okay. So the main idea is actually to show you that this kind of equation come, and we can solve this kind of equation by separation of variable. So once we solve this by separation of variable, we'll get this function. So this sine lambda nx, and these are the eigen function. Okay. So here similarly this is the solution. So this is the technique, is nothing but the separation of variable I am using. This is some result. This is actually streamline, mean you can say this is the flow phenomena. So there is a gap, right? So in the bed and object there is a gap. So in the gap it is saturated with water. So when the gap is very small, then this water from sea cannot come. So how this gap will be saturated? So this porous bed, or rather say soil, this will transfer the water into this gap region, and the gap is very small. Okay, so suppose this is the gap width. So when the gap is small, so it flow is coming in this region vertically. So the streamline is vertical. But when we increase the gap, so sea water will come into account. So according to the flow will look like this. Okay, that is the flow phenomena. Similarly, here we have discussed the how much force it is required. So we can see that for a gravel we need less force, but if the means sandy bed or the seabed is consist of silt or clay kind of thing, then we need means large amount force. So this kind of thing actually gives us an idea or a priori estimate about the time constant, amount of force, or how many equipments we required actually. So that's the thing. So this is the linear configuration. So let us talk about some nonlinear configuration, how to solve. Okay. So for the timing, let us take a linear ODE and try to understand what is the perturbation technique. So suppose consider ODE where epsilon is a small parameter, very, very less. What is the idea? Actually, we will assume this kind of expansion in terms of epsilon, and we will substitute in the main ODE. So once we substitute in the main ODE, so we will get corresponding this equation. So if we collect the corresponding each similar power, so we will get this kind of ODEs. Okay. So once we solve this ODE, y1, y2, y3, then the sum will be the solution. Okay, so if we take more term, then the accuracy will be more. So this is the idea behind perturbation. So this perturbation theory helps us to solve a problem in nonlinear configuration. So suppose we are talking about this kind of flow through this wavy channel. Okay, so here the configuration is nonlinear. This is bounded by two wavy wall. So how to solve? So here we will apply perturbation technique. So what will be the perturbation parameter? So we assume that mean width by the wavelength, or B by L. So that is very, very small. So that actually allow us to apply perturbation theory. So this is the governing equation. So what we'll do, because since it is configuration is nonlinear, so we'll expand. So here this is a small quantity. So correspondingly, we have unknown UP, VP, and P. So we'll expand like this. So this is called a regular perturbation. So once we expand and we collect the similar power of delta and solve the corresponding subproblem, then finally we'll add, we'll get the solution. So here we'll get, if we flow, it looks like this. So here some trap will be there, some circulation zone will be there. So now where we can apply this kind of thing? So this kind of thing we can apply for storing our means this carbon dioxide. So nowadays the carbon dioxide actually is increasing in the environment. So this is a new way, we call it as a carbon capture and storage, how to mitigate the carbon dioxide or how to store the carbon dioxide from environment to some inside groundwater. So what is the procedure? Actually, we inject CO2 in the critical, supercritical CO2, that means the liquid CO2 through a well. Now you can see, since this trapping phenomena occurs, so accordingly in the inside some rock that is almost impermeable. So here this trapping will help us to allow or store this carbon dioxide. Okay, so this is the application of nonlinear configuration, right? So these are some references. Thank you.
Thank you, Timir. Dr. Karmakar. I mean, it was a wonderful session. People have also expressed, that they have liked it and they have put some comments. And at first, I would like to let you know that our students will be very much benefited because, you know, in the new CBCS syllabus, some PD, I mean, Shubhankar teaches them. I think Shubhankar, you are teaching them the Lagrange method and Charpit method, right? Jacobi method is not included in the syllabus in new CBCS system.
Right.
So they will be very much benefited from your talk because you have introduced Jacobi method to them. So I would like to, request you whether you can once again just repeat that part where you have explained what is the main difference between Jacobi method and Charpit method. What is the main difference in 1-2 line? Would you please repeat that one so that our students will get the idea?
Yeah. So I'm just going to the main slides, okay? Yeah. So, am I audible?
Yes, very much.
Yeah. So, actually, this Charpit method and the PD, actually, it has two independent variables. Okay. Suppose it has two independent variables, that means of the form f of xy z pq, right? That means z is the dependent variable, xy is the independent variable. Then we can apply Charpit method. Now, suppose it is a first order PD, but it has more than two independent variables. Then we cannot apply Charpit method because Chakraborty method is mainly confined to two independent variables. So for that, when it has more than 2 independent variables, let us say 3 independent variables, and the PD is of this form, then we have to apply Jacobi method. So now this kind of PD we cannot solve by Chakraborty method. So that is the main thing. Now how we can solve this kind of PD? For that we need some auxiliary equation like Chakraborty or Lagrange's method. Like, so each method we have, like Lagrange's method, we have Lagrange's auxiliary equation. In Chakraborty method, we have Chakraborty auxiliary equation. So how to obtain this Jacobi's auxiliary equation? So to obtain the Jacobi's auxiliary equation, actually, we need the idea of compatibility. So now, what is the idea of compatibility? So when we say two PD is compatible, F and G, so the compatible means they will share a common solution. Okay. So now this idea actually allows us to find the Jacobi's auxiliary equation. Right. So suppose we want to solve this equation. So what is the idea? We will find two PD, one parameter. Those are compatible with F. Okay. Now those are compatible with F. So correspondingly, we will find, using that compatibility, we will find Ux, Uy, and Uz. And once we have Ux, Uy, Uz, we can find U. So this is the compatibility condition. That means if H1 and H2 are compatible with F equal to 0, then we have this. Okay. Now this if we split, means split, then we have this. So this we can see this is a generalized form of quasi-linear equation. Like Lagrange's method, we have P plus Q equal to R. So what is the corresponding auxiliary equation? Dx by P equal to dy by Q equal to dz by R. So this equation is also the same kind of equation, quasi-linear kind of equation. So instead of dx by P, we have Fux. Dy by Q, we have Fuy. Right? So similarly, this. So once we have this Jacobi's auxiliary equation, now we have one auxiliary equation like Chakraborty or Lagrange's. So this is our aim. Once we have this Jacobi's auxiliary equation, we can solve this Ux, Uy, and Uz. So once we solve Ux, Uy, Uz, we can just solve the PD. The idea, suppose this is the PD. So now here you can see that how many independent variables is there? X and Y, and J is the independent variable. So you can apply Chakraborty method, no problem, right? But we can see that if we apply this Jacobi's method, we will get the same solution what we obtain from Chakraborty method. So instead of directly applying Chakraborty method, what we are doing, we just verifying. So we are reducing this PD to a PD where it has more than 2 independent variables. So it has actually, it has 2 independent variables X and Y. Now substituting this, it can be think as a PD which has more than 2 variables, X, Y, Z, 3 independent variable, and U as the dependent variable. So we had X and Y independent variable, Z as the dependent variable. Now we have X, Y, Z as the independent variable, U as the dependent variable. It can be thought as right this. So now this is actually suitable for applying Jacobi's method. Okay. So once we apply this Jacobi's method, we'll get finally this solution. Now you can check this same solution can be obtained by Chakraborty method also. But what is the main need of Jacobi's method? It can actually gives us a solution of a PD where more than 2 independent variables is present. So that is the idea, I think.
Dr. Karmakar, there is another question from Subhash Mondal. He asked, how do we represent higher order PDE geometrically? Means elliptic, parabolic, hyperbolic. Is there any geometrical interpretation, or you have already told there are algebraics? I mean, some similarities.
Yeah, equation actually, as in the first slide we have discussed, that if we want to discuss a PD geometry, so means not only geometry, it can be along with the geometry we have to discuss with some physical sense also, like this. So this here, this is the PD. This we call it as a wave equation. Okay, so what is the wave equation? Actually, the formation of wave. So when you throw a stone into a pond, so here we can see that this kind of wave, this kind of wave is formed, right? So in terms of geometry, you can think as the spherical wave is coming. So the coordinate system you can discuss by the spherical coordinate system. In physical sense, you can say that the wave is formed, and after some time, it's just the strength of the wave is reducing, or after some time, it is going to some steady configuration. Okay, so that is the, if we want to discuss a PD, okay, but the partial derivative we want to, if we want to discuss geometrically. Okay, the partial derivative, actually it is some sort of directional derivative, you can say, right? Like ordinary
question was, I mean, second order PD you have already discussed, elliptic, hyperbolic, and parabolic. Is there any geometrical interpretation that he asked? And I mean, in your talk you have already told that there is some similarity algebraically.
Yeah. Algebraically means, see, this kind of PD, actually this has a resemblance to its quadratic form. Okay, ax square plus b xy plus cy square plus dx plus ey plus equal to g sum. So this, due to that resemblance, actually this terminology came, parabolic, hyperbolic, and elliptic. Of course, you can means describe by geometric form also. So for that you need to actually discuss by method of characteristics. So once you have the characteristic of a PD, then by that characteristic plane means you can discuss what kind of behavior the PD will have. So that for that you have to actually means I need some board, so that will be okay. Means, otherwise,
okay,
actually the main.
Due to shortage of time, I will take last question, which is very small question. That is, you have mentioned separation constant K. You have taken negative, associated to ice melting phenomenon. So why did you take K negative? In a few words, could you explain? Just.
Yeah. So actually, the idea behind taking K as negative is actually we want that as t tends to infinity for larger time configuration, so it will independent of time, right? That means it will reach a steady state. Okay, steady state means it will no more depend on t. That means suppose we drop a ice, then after some time it will totally melt down. So it will now the heat transfer will not happen. Okay, when it is in the like ice, it is solid and liquid. So there is, so until that much time it will, the phenomena will go until the ice totally melt down. Okay, so that time we can see large time. T tends to infinity means here we can consider it as some critical time or large time. After that, there's no, means it reaches steady state. Okay, so steady state means in this configuration, if we take minus lambda square, then this t Pd we will get e to the power minus lambda square t. Actually, our main thing is e to the, we want a Pd means solution as exponential minus lambda square t. This negativity, why? Because as t tends to infinity, e to the power minus t reaches to 0. Suppose if we take e to the power plus lambda square t, then after t tends to infinity, it will never reach the steady state. That means the if even though we are putting ice, it will means after infinite time also nothing will happen. Means it will never make into liquid. Or suppose you means string, if we take if we means string, pull a string and just leave, then it will just oscillate. But after some time it will be steady. Okay, so that's why e to the power minus t. So since this minus thing is coming because of this minus lambda square.
So this negativity part will come to the power of the exponential, which will make it to 0 when
zero.
It ends
bounded. Solution is bounded. Otherwise, it will be unbounded.
Okay. We have another session. So first, I would like to thank Dr. Karmakar for his invaluable speech, and our students rather, and not only students, whole audience will get benefited. And my last request to you that some people have already asked for your PPT. I don't know whether it will be possible for you to provide it. So if you will give us, we'll send them. That's all. And thanks again. Now we will move toward second session where we'll have Dr. Pavel Pal from Bankura University. I'd give my baton to again our convener, Dr. Shubhankar Saha. He will introduce Dr. Pavel Pal, and we'll move to our next session, which will be based on algebra. Okay, thank you.
Thank you, Dr. Timir Karmakar, and thank you, Shubro. And now I am introducing Dr. Pavel Pal from Bankura University. Dr. Pavel Pal presently is a faculty member of Mathematics Department in Bankura University. He did his PhD from Jacobi University in pure mathematics. He also worked as an assistant professor in Government General Degree College in Singur and Purulia JK College. Besides his passion of teaching, his current research interest is semi-group theory and near algebra. He has published several research articles in reputed international journals like Semigroup, Forum, Communications in Algebra, etc. So I would request Dr. Pavel Pal to start his lecture.
Thank you, Shubho. Good afternoon, everybody. First, am I audible clearly?
No, it's not audible, Pavel.
Not clear. The sound is not clear, no?
No.
Okay.
I would like to.
I think it's clear.
Place your mouthpiece in your mouth, nail your mouth.
Okay. Now it is. Is it clear? My sound is clear.
Yeah, it's okay.
Okay. So good afternoon, everybody.
Okay.
First, I want to. Yes, Shubhra, do you want to say something?
No. You can start. We are leaving the screen, and the screen is yours. Okay. Start your presentation.
Yes. First, I want to thank the organizers, that is the IQAC and the Department of Mathematics of Sir Gurudas Mahavidyalaya. In the one thing I want to mention here, in the current pandemic situation, there is no other way except those kind of webinars or webmates to meet academically. But we have to keep in mind that the total online teaching procedure is creating a new divide in the academia. Nothing else I want to mention. Here I'm going to start. I'm going to start my lecture, whose title is Modules and its Application in Describing Canonical Forms. Keeping in mind the nature of the audience, where mainly the lot of participants are students. So I start here with some basic notions of module theory, and then I'll discuss the connection between the modules and the canonical forms of linear operators on vector space. Okay. So what is a module? So before get the before going to the definition of module, first I want to mention that I think all of us know what is the group action. Here. Group action is it is a mapping. It is a non-empty set, and this is a group. So group action is nothing but a non-empty set with action by a group, and action means it is a mapping which the pair G comma S, this pair goes to G dot S. The action will depend on the corresponding problem, and this mapping will satisfy two equations, two conditions. One is this, and second one is so first one is it is compatible with the identity, and the second one is the action is compatible with the multiplication of the group. That means the binary operation of the group. Now, in this definition, if we replace this S was only a non-empty set. If we replace it by an abelian group, and if we replace the group G by a ring, then the resulting structure, and if that correspondence, the mapping preserves all kind of compatibility of the action with all of the binary operations of that abelian group and the ring, then the resulting structure will be called a module. Here I'm giving the formal definition of the module. Suppose R be a ring and left R module is nothing but a abelian group M plus with the action R cross M to M, and will satisfies those conditions. The first three conditions clearly we can understand. This is the compatibility of the action with respect to the operation. First two is the with respect to the operations of the ring R, and the third one is the compatibility of the action with respect to the binary operation of M. And the fourth one is if R has identity, then it will preserve that compatibility. Okay. And here the action R is acting from the left side, so we call it a left R module. Similarly, one can right R module. So theory of left R modules and right R modules run actually parallelly. So here we always mention, if unless mentioned otherwise, we always take left R module. Now, if we look at the definition of module, we see that R module can be viewed in an easier way, because if we look at the properties, we see that those properties are actually the properties of the vector spaces V over F. Okay, because vector space is nothing but V is nothing but an abelian group, and there is an external multiplication by a field. Here we take a ring R instead of a field. That is the difference, nothing else. Okay, so we can think modules as a generalization of vector spaces, as rings are generalization of field, nothing else. So naturally we can define substructure of module, which is nothing but subgroup N of M, which it satisfies, which preserves the action of the main module M. Okay. Now I want to give some basic examples which are actually the motivating one, which will be the most natural example of a module. If we take a ring, I have nothing else, just I have a ring. Then that ring R itself becomes a left as well as right module over R. So the ring is R and the module is also R. So R is a R module, and the submodules of R then becomes precisely the left ideals of R if we take it as a left R module, and if we take it as a right R module, then submodules becomes only the right ideals of R, precisely the right ideals. Now the second motivating example is, suppose I have only an abelian group in my hand, nothing else. Then can I give it a module structure? The answer is obviously yes. any abelian group becomes a Z module structure, becomes a Z modules. And the here the action, the mapping is n comma a goes to na. Na means a is operating itself n times, and submodules of any Z modules of G are precisely the subgroups of G. Okay. Now, this example we have already discussed a little bit of it. Suppose I have a field in my hand, okay, F, and a vector space V over F. Then this vector space V becomes an F module. It is very clear from the definition, and the submodules of V are precisely the subspaces of V. Besides that, one more important observation is there. The set of all modules of a field, suppose only a field F is given to me, then the set of all modules over that field F and the set of all vector spaces over the field F, these two sets become same actually. That means if we take any module over field F, it becomes a vector space over F, and if you take any vector space over F, it becomes a module. So one question naturally comes in our mind, that is there at all any difference between a module and a vector space? Obviously that question comes in our mind. So to clarify this question, we now define some basic notions of modules first. Okay, so just like vector space, first question is how do we define linear combination in an R module? So just like vector space, the linear combination of any finitely many elements m1, m2, mk of n is nothing but the R linear combination of m1 to mk. That means r1 m1 plus rk mk, where the coefficients are coming from R, and in the vector space they are coming from F. That is the difference till now. Similarly, how can you define a spanning set in R module? An R module M is called spanned by a subset A of M. If span A becomes M, so span A means what? Span A means this set, summation AI plus summation Ri xi finite sum. The second term is, I think we know that term because it is nothing but all kind of linear combination of the elements of A. Okay, the first term is new to us. It comes actually for the absence of unity in R. If the ring, the M becomes R module, so if the ring contains identity, then this term will be omitted because the second term contains the first kind of terms. Okay, then span A will be only summation, the only all kind of linear combinations of elements of A. That is only the difference. So the next question is, how do you define finitely generated R module? Finitely generated R module is nothing but a module which has a finite spanning set. Okay. And how do you define a cyclic module? Cyclic module is nothing but a module which has a spanning set with cardinality 1. That means a module can be, if a module can be spanned by a single element, then it is called a cyclic module. The nomenclature is very clear. It is clear from the group structure. I think cyclic subgroup means it has one generator. This kind of definition. Now, how to define linear independence here? Linear independence is also similar to the vector space. If we take a non-empty set S, then it will be called linearly independent if we take any finitely many elements of S, and if any linear combination of those elements becomes 0, then if the coefficients become 0, and it is true for all kind of finitely many subsets of S, then the set is S is called linearly independent. Otherwise, we'll call it linearly dependent. Okay. So this definition also here, only the difference from the vector space is the coefficients are taken from R instead of a field. So just Similarly to the definition of basis of a vector space, here we also define basis of a module. It is nothing but a subset of the module which is linearly independent as well as spanning. Okay, and if a module has a basis, it is called a free module. Now, now we observe that some comparative study between modules and vector spaces, and in our coming pathologies, we see that in the process of generalizing vector spaces to the modules, some very important properties are lost. In a vector space, the first pathologies in a vector space, we know that in a linearly dependent set, any element can be expressed as the linear combination of other elements. But is it true in our module? The answer is no. We take for example, we take the Z module Z. Now we take the subset S, which contains only 2 and 3. So first we observe that this set is linearly dependent because it has a linear combination which is 0, but the coefficients are not 0. Which is that the answer is 3 into 2 plus minus 2 into 3 becomes 0. So that set becomes linearly dependent. But can 2 be expressible as linear combination of 3, or 3 can be expressible linear combination of 2? Both the answer of these two questions are no. We all know 2 cannot be expressed as an integer multiple of 3, or 3 cannot be expressed as an integer multiple of 2. The next pathology is in a vector space, we know that a minimal spanning set is always a basis. But here, the same example which I took in the previous pathology, same example, we see that this is a spanning set. We already see that because it contains 2 and 3, so it contains 1, so it spans Z, but it is not linearly independent. We have already observed, so it is not a basis because it is not linearly independent, and it is also minimal because if we remove 2 or 3, any one element from this S cannot span the whole set. In a similar fashion, we see that a maximal linear independent set in R module is not a basis, which is actually true in a vector space, but the answer is no in R module. Here we take the R module Z cross Z2 over Z. The M is Z cross Z2 and R is Z. Now I take the singleton set 1, 0 bar. Clearly it is linearly independent. Clearly it is linearly independent. Since n into 1, 0 bar becomes 0 because n is 0 in the for any n it is 0. If n into 1, 0 becomes 0, 0, so it becomes n is 0. So it is linearly independent. But it is not. It fails to be a basis because it doesn't span the whole module Z cross Z2 because 1, 1 bar is not in that 1, 1 bar doesn't belong to the 1, sorry for interruption. 1, 1 bar doesn't belong to the span of T. Okay. Now the next question is, we all know that each vector space, I think there is a sound problem. All of you can hear me. My sound is in highest position. One second. I want to speak loudly. Okay. We all know in a vector space, any vector space has a basis. We all know and we read in graduation, but the striking difference, one very striking difference between modules and vector space is each module need not have a basis always. The example for is that the example not is a very easy one. If we take the module Zn, Z module Zn, the module is Zn and R, the ring is Z. Okay, then as any element A belonging to Zn becomes 0 if we multiply it by n, then so any singleton element A in Zn becomes linearly dependent. So can it be, so there is no linearly independent subset of Zn, so it doesn't have a basis. Okay. The next problem is, the next pathology is, if R module M has a basis, then its submodule need not have one. Obviously, the answer is true in vector space, because any vector space has a basis. So any subspace itself a vector space, so it has a basis always. But the answer is not true in R module. We see that, so obviously R module of a submodule of a free module need not be free always. If we take the ring Z root minus 5 and if we take R module R, then it becomes free. It is generated by 1, the basis is 1. But if we take the submodule or the ideal, which is generated by 2 and 1 plus root minus 5, is it doesn't have a basis, because a singleton set, if we remove any one of them, this is a linearly dependent set, 2 and 1 plus root minus 5. But if we remove any one of them, it cannot span the whole ring or whole module. So it has no basis. Now, here it is written that any R module can have basis with different cardinalities. Just look at that statement. One expression comes in my mind. What, is it really possible? But yes, this is possible in R module, in module theory. If we take an infinite dimensional vector space over a field K, then the set of all endomorphisms becomes a ring. We all know that. Then that ring R over R becomes a module. For that modules, actually, for any positive integers a, positive integer n, Rn becomes isomorphic to R. So R becomes free, and it is Rn. It is true for any positive integer. So any positive integer n, R module R has a basis with cardinality n. So this, so that means if I say particularly that ring has a basis with 2 elements as well as a basis with 3 elements, etc. If you give any positive number n, I can give you a basis with the cardinality n of that ring. Okay, that very important of that, this observation actually leads to a very new research area, which is whose name is Leavitt path algebras, and it is a very booming one. Now, next pathology is submodule of a finitely generated R module need not be finitely generated. If we take a field K and take a set X, which contains infinitely many variables, then the ring K third bracket X becomes a module over itself at module R, and clearly it is cyclic and finitely generated. Obviously, it is finitely generated by 1 itself, because any R module R is cyclic. It can be generated by 1 itself. But if we consider the submodule S of R, which consists of only those kind of polynomials of R where the constant term is 0, then this submodule is not finitely generated. We cannot construct a subset of this S where a finite subset of S which can generate S. Okay, and similar and same example gives us this result, that submodule of a cyclic R module need not be cyclic always. Now I'm going to my next section, and is in this section our main target to find how the various canonical forms, namely rational canonical forms and Jordan canonical forms of a linear operators to come with the help of modules. The terms Jordan canonical form and rational canonical forms are known to I think all of you, all of the students, I think, know those kind of terms, graduation as well as master students. But here I want to explain how these canonical forms actually come with the help of modules. So for that, first I want to mention some 2 or 3 basic notions. First one is I want to define torsion element in a module. We know torsion element in a group. Uh, um, an element is torsion which is finite order. Now, torsion element, so similarly, we can define torsion element in a ring. And similarly here, we define a torsion element in a module, m, small m, belonging to capital M is called a torsion element if there is a non-zero R such that Rm is equal to 0. And the collection of all torsion elements of a module is called, is denoted by tor m. And if R is an integral domain, then this theorem becomes a submodule of M. And a module, an R module M is called a torsion module if M becomes torn. That means all the elements of M becomes torsion element. Now, motivated by the structure of quotient group or quotient ring, here we can define the structure of quotient module. For that, we take a submodule n of M, and we can define an action of the group M by n by the ring R. In this way, R into M plus n is equal to Rm plus n, which becomes also also an R module, and it is called quotient module. And for any submodule n of R, the annihilator of n is the collection of elements of R, which actually annihilates all the elements of n. That means the collection of all small r such that Rn is equal to 0 for all n. And this the set annihilator of n becomes an ideal of R. Okay. Now comes the main theorem. This theorem actually is the pivot to describe the canonical forms of a linear operator over vector spaces. Here we take a PID. I think all of you know PID, which is PID is. PID is an integral domain where all the ideals can be generated by a single element. Okay. Here we take a PID, and we take an R module which is finitely generated. Okay. Then that theorem says that M is isomorphic to the direct sum of finitely many cyclic modules. More precisely, M can be isomorphic to RT direct sum. First, I want to mention what is RT. RT is nothing but R direct sum T times. That means there is T number of copies of R, and the other part is direct sum of R quotient submodule generated by A1 quotient, direct sum R quotient general A2 dot direct sum R quotient AM. So where T is a positive integer and A1, A2, AM are non-zero elements which are not units in R, and the most important one is they satisfy A1, A2, AM. They satisfy the divisibility relation. A1 divides A2 divides AM. Okay. So from that decomposition, we can observe that M can be decomposed in a free part and a torsion part. The first part, RT, is a free part. Okay, it is the free part of M, and the remaining part, that means R quotient A1, direct sum R quotient A2, direct sum R quotient AM. This is the torsion part. So Rm torsion free. If M is torsion free, then M is free. Free means because then M is isomorphic to only RT, and RT means free. This is the free part of M. And by the third condition, third result of that theorem, it says that torsion tor M, that means torsion part of M becomes the last part. And if M becomes a torsion module, that means M is equal to tor M, then the free part becomes 0. So there is no r to the power t part, and only so t becomes 0, and only M, then M is equal to tor M will be isomorphic to the last part r quotient a1 direction r quotient a2 dotted r quotient am. And in this case, annihilator of M becomes the ideal generated by the last factor am. And I want to mention here that those factors, those those elements of R, A1, A2, AM are called the invariant factors of M, and the small t, this small t is called the free rank or the Betti number of the module M. So t is called the Betti number, and this A1, A2, AM are called the invariant factors of M. Okay. So with the help of the above theorem, now we are ready to formulate one of the canonical forms of a linear operator of a vector space. So first we observe that suppose we take a vector space over a field F, then this vector space V becomes an fx module. Okay, and the action, the mapping of the module is this fx cross V to V, and the mapping goes to the pair fx comma v goes to fx dot v. And how does the action is defined here? The defined here, it is fx dot v is equal to ft of v. Ft of v means what? Ft of v means ft is what? It is an operator because we replace t in the place of the variable x in the polynomial. So it becomes a0y plus a1t plus a2t square, like that, and it becomes another operator, and it is operating on the element v. So fx dot v, the action is defined in this way, that it is ft is operating on v. So with respect to this action, the vector space becomes an fx module. Okay. Now canonical, what is canonical form of an operator? Canonical forms means canonical form means, suppose an operator is given, first we calculate its matrix, and we see that the matrix of this operator is similar to an easy matrix, like a easy one, like a diagonal one, or a matrix where upper diagonal or lower triangular rectangular parts are 0, like that. So for that, what we took a vector space over F and a linear transformation, linear operator on V, and obviously as we find the matrix of T, so obviously we take the vector space finite dimensional. So here we take the vector space V as n-dimensional vector space over the field F and take a linear operator T. Okay. As F is a field, then Fx, that ring, becomes a PID. We know F is field if and only if R is field if and only if Rx is PID. So Fx is a PID, and as V is finite dimensional vector space, so V becomes a finitely generated R module, because that basis can span the module also. So V becomes a finitely generated R module. So V actually satisfies, V as module, as Fx module, satisfies the hypothesis of that theorem. Here we take R being PID and M being finitely generated R module. So here Fx is an PID and V is a finitely generated Fx module. Okay. Now by that fundamental theorem, previous theorem, we have the following decomposition, that V can be expressed as V, free part of V and torsion part of V. Now we observe that in this case, in this particular case, this module becomes a torsion module. Not every module torsion module, but here that vector space, in vector space over Fx becomes torsion module if the vector space is finite dimension. Okay, how for torsion module we have to show that each module is torsion element. That means there is an element of the ring which annihilates V. Okay, for each V. Now, do you know what is minimal polynomial for each linear operator? Minimal polynomial for linear operator is least degree monic annihilating polynomial. That means a polynomial which is monic, which annihilates T, and between all the monic annihilating polynomials of T, this is of least degree. Okay. So if we take the polynomial mx, clearly it is a non-zero polynomial. Nothing, there is no doubt about that. And here, as it is annihilating polynomial, annihilates T, so mt is a zero operator. As mt is a zero operator, so mt after operating on V becomes zero for all V because it is a zero operator. Okay. So each element can be annihilated by this non-zero polynomial which belongs to fx. Okay, so it is clear that any element is torsion element, so V becomes a torsion module, so V is equal to tor V. Okay, this, so there is no free path. And another observation here I want to mention that the set of annihilator V, what was the definition of annihilator V? The elements of R, that means here the elements of fx, which actually annihilates all the elements zero. So if we take that set annihilator V, it is generated actually by the minimal polynomial of T, which is clear from the definition of minimal polynomial. Okay. Now, by the fundamental theorem, here we have already observed that the module is torsion module. V is a torsion module, so there is no free part. Only V is equal to tor V. So R to the power T, that factor is vanished. So there is only the last part. So we put V and Fx in the place of M and R in the main theorem, and we obtain this theorem. V is isomorphic to fx quotient small f1x dx sum fx quotient small a2x. Quotient is not only f1x, it is ideal or submodule generated by f1x. Okay, and each of the polynomials f1x, f2x, fnx are monic polynomials with degree at least 1. That means they cannot be constant one, and they satisfy the divisibility relation between them, which is f1x divides f2x dot fnx. Okay, and the third condition of the theorem, we have observed that annihilator of M was the ideal generated by the last factor. Here the last factor is fm, so annihilator becomes the ideal generated by fm. And we have already observed that annihilator becomes the ideal generated by the minimal polynomial. So minimal polynomial and the fm actually becomes associate, and as they are monic, so fmx is equal to mx, nothing else. So the last factor of those invariant factors, fmx, actually becomes the minimal polynomial of the linear operator. Okay. So finally, we got the decomposition of V in this way. And now we concentrate in the matrix decomposition, that means in the canonical form of T. Okay, so if we take a basis B1, B2 of each direct summand, that means we take a basis of this vector. This is a vector subspace. This is a submodule of V as well as a vector subspace of V. So suppose we take a basis B1 of this subspace and B2 basis B2 of this subspace, basis Bm of this subspace, and if we write them along, that set B1, B2 dot Bm gives you a basis of the total vector space V. So if you give me basis for each direct summand, then we can give, then I can give you a basis of V. Okay. And suppose without loss of generality, I take the kth direct summand. That means capital Fx quotient ideal or submodule generated by small fkx. Suppose small fkx is a polynomial with degree rk. Without loss of generality, there is no importance in taking rk. It is taken arbitrarily. Fk is the polynomial of degree rk and monic polynomial of degree rk. So it can be written as a0 plus a1x dot 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 a rk minus 1 into x rk minus 1 plus x rk. Okay. So by the construction of the vector subspace fx quotient fkx, we can see that this gives you a basis of this vector subspace. Here we take that basis bk, 1 plus this, x plus this, x square plus this. Okay, that means because each element is in the form some polynomial fx plus this, it is a quotient module structure. So we can write them in a bar notation. 1 bar means 1 plus the quotient module, x plus the quotient module in this way. Okay, x bar is equal to x plus this. So we take that basis 1 bar, x bar square dot dot x bar rk minus 1. Why this is the highest degree in the basis? Because if we take further power of x bar, suppose if we take x bar to the power rk, then in terms of fkx we can write that element with the linear combination of the remaining one, so it becomes a linear dependent one, so it cannot be in a basis. So 1 bar x bar dot dot up to x bar to the power rk minus 1, those elements give you a basis of the kth direct summand. Okay. Now just think, how do we calculate the matrix of a linear operator on a vector space, arbitrary vector space? We take a finite dimensional arbitrary vector space and take a linear operator. How do we get the basis of T? First we take how do we get the matrix of T? First we take a basis of this vector space, and we operate T on the elements of the basis. Suppose b1, b2, small b1, small b2 are the elements of the basis. Then we calculate tb1 and we see tb1. How can tb1 be expressed as the linear combination of b1, b2, bn, and that linear combination, the coefficient will give you the first column. Similarly, tb2, the linear combination, how we express tb2 in terms of b1, b2, bn, give you the second column in this way. So the matrix comes to us by operating T on the elements of the basis. So here also we operate T. Here T is defined on V. Here actually we take the operator T restricted on the kth subspace fx quotient fkx, and this or the matrix of that operator T restricted on the kth subspace with respect to the basis bk, which we have already taken, can be obtained by operating T on the elements of bk. Okay, so now we check how does T operate on the elements of bk. For that we again take the help of the module structure of V. We know that fx dot v, that action was defined in this way, ft of v. Now here we have to calculate for any small v belonging to bk. We have to calculate what is the value of tv. Tv means ultimately becomes tv is equal to x dot v, because just look at the module action. How did we give the module structure on V as fx module? The action was fx dot v is equal to ft over v. So t over v becomes x dot v. So here the for observing operating t on the elements of bk, it is enough to observe how does x act on the elements of bk. So first element of basis is 1 bar. So after, in this slide, I show you how does x act on the elements of the basis bk. So after operating on 1 bar, it becomes x bar. After operating x bar by x, it becomes x bar square. So similarly, x bar to the power rk minus 2 becomes x bar to the power rk minus 1. So in this way, we get x bar to the power rk minus 1 is equal to x bar rk. Before the last line, all the elements on the right side, right column, x bar square, are in the basis. Only the last element is not in the basis. So we have to express it in terms of the basis element. Here we calculate x bar rk can be expressed as minus a0 1 bar minus a1 x bar minus a2 x bar square dot minus a rk minus 1 into x bar rk minus 1, where 1 bar x bar dot x bar rk minus 1 are in the basis, and these coefficients actually we are taking from the polynomial fkx. So finally, from the first correspondence, we see that what will be the first column of that matrix. So it is 1 bar goes to x bar. So it is actually 0 into 1 bar plus 1 into x bar plus 0 into other elements. So first column of the matrix becomes 0, 1, 0, 0, 0. Similarly, second one becomes 0, 0, 1, 0, 0, because it is x bar goes to x bar square. So 0 into 1 bar, 0 into x bar, 1 into x bar square, and 0 into other elements of the basis. Similarly, x bar rk minus 1 goes, x bar rk minus 2 goes to x bar rk minus 1. So all the other elements are 0. So there is 0 in those positions, and only 1 in the last position. And x to the power rk minus 1, the last element, goes to this. So if we put it in the column, the last column is minus a0, minus a1, minus a2, dot minus a rk minus 1. So it is actually the matrix of T restricted on the kth summand, the kth direct summand with respect to the basis bk. Okay. So can you recognize this matrix? I think many of you can recognize this matrix. This is actually companion matrix for the polynomial. This here we observe that how does the companion matrix come with the help of module. For just reminiscing, here I give the formal definition of a companion matrix. If I take a polynomial ax is equal to x to the power k dot this be any monic polynomial, then the companion matrix ax, which is denoted by cax, is the following matrix, where only the last column is consisting the coefficients of that matrix. Here one mistake is there. This will be a1 and a0. So the last column is the negative of the coefficients of the polynomial, and the other column only contains 0 and 1, only 0 and 1. 0, only 1 in the position next to the position of that column. Okay, it is the first column, so 1 is the second position. It is the second column, so 1 is the third position. It is the last but 1 column, so 1 is the last position. This is the companion matrix for any polynomial which is denoted by cax. Okay, so we observe that now we observe this. So we have to find ultimately the total matrix of T. Here we have already obtained only the kth part of that matrix. So one thing I have to mention that each direct summand is a T-invariant subspace. What is T-invariant subspace? And subspace W of V is called T-invariant. Is T of capital W is subset of W itself. That means if we operate T on any element of W, then the image remains in the subspace W itself. So by that observation, we can see that the matrix of T with respect to the basis, which is actually B1, B2, Bm, that basis is the direct sum of the matrix representation of T restricted on each direct summand with respect to each basis Bi. So ultimately, the matrix will become in the block diagonal form, where each block contains the companion matrix of the corresponding direct summand, which is Fi. So here I show the final matrix. So first invariant factor was F1. Here it is the companion matrix of F1 in the first block. Say it comes from the first direct summand. It is the second block. Second block is the companion matrix of the second invariant factor F2. In this way, we get the last block is the companion matrix of the final direct summand Fm. Okay. So this is actually the rational canonical form of T, whose name I think is familiar to all of you, and I think many of you can calculate how does the rational canonical form of a linear operator come. But here I wanted to show the formulation of rational canonical form, and one observation is there: any two similar operator, that means if any two matrices, because operator and matrix on a finite dimensional vector space, these two notions are actually equivalent. So any two matrices are similar if and only they have same rational canonical forms. Okay. One observation is very important here. We have already observed that the last invariant factor is the minimal polynomial itself. Now, if we observe, if we look at the companion matrix of AX, and if we calculate the characteristic polynomial of this companion matrix, we see that characteristic polynomial of that matrix itself is AX itself. Okay. So characteristic polynomial of CF1x is F1x. Characteristic polynomial of this matrix is F2x. Characteristic polynomial of last factor is Fmx. So what will become the final characteristic polynomial of that final rational canonical form? It becomes F1x into F2x into F3x Fmx. So finally, we got the characteristic polynomial of the rational canonical form is F1x into F2x Fmx. That is the product of all of its invariant factors. And already we know that the last factor is Fmx. With the help of these two observations, we can actually do many kind of problems regarding rational canonical form. Here I want to show one kind of problem. There are many types of problems here, but lack of time, I just want to show one kind of problem. Suppose T is a linear operator over a vector space whose over R, over the field R, and the dimension of vector space is 6. That means the vector space is isomorphic to R6 over R. With suppose it is given that the characteristic polynomial is x minus 2 whole square into x minus 1 whole to the power 4, and the minimal polynomial is x minus 2 into x minus 1 whole square. So by our previous discussion, we can have that direct sum decomposition of V, and in terms of invariant factor decomposition, where invariant factors are F1x divides F2x Fmx, such that their multiplication is the characteristic polynomial and the last factor is the minimal polynomial. So keeping in mind these two relations, that their multiplication is characteristic polynomial and the minimal polynomial is the last factor, we can have only two type of there are possibility of two kind of invariant factor decomposition of T here. Okay, so problem to problem, these possibilities may vary. Maybe there is only one factor decomposition for any set of characteristic polynomial and minimal polynomial. Maybe there are many other options, but in this problem, there are only two kind of invariant factor decompositions of T. Okay. So one is clearly so last factor is x minus 2 into x minus 1 square. So we have to calculate the previous factors. The previous factors may be written either x minus 2 into x minus square itself as multiplication of these two factors becomes you the characteristic polynomial, and in other way we can calculate we can decompose those invariant factors in this way, that x minus 1 divides x minus 2 into x minus 1 divides x minus 2 into x minus 1 square. So corresponding these two type of decomposition, so we will get two kind of non-similar rational canonicals form. So first I calculate the first one. So for first one, I have to calculate the companion matrix of this invariant factor and then the companion matrix this invariant factor. Luckily, both the factors are same. So I calculate the companion matrix of this, which is nothing but the polynomial this, and whose companion matrix is this. The first two columns are very easy. In the last column, we'll just put the factors negative of the coefficients and the rational canonical form of T for the first decomposition is it is CF1x and it is CF2x. As both of the factors are same, so rational canonical companion matrices are also. Now we get the second one. So for this one, I have to calculate companion matrix of this, companion matrix of x2 minus x1, and companion matrix of this. So companion matrix of x minus 1 is nothing but a 1 cross 1 matrix consisting of only one there. Okay, it is the coefficient. So I have to calculate companion matrix of x minus 2x and x minus into x minus 1, and companion matrix of x minus 2 in x minus 1 square I have already calculated. So companion matrix of these two polynomials will give you our second rational canonical form. This first one is the companion matrix of x minus 1. This is for the companion matrix of x minus 1 into x minus 2, and this is for the last one. So for this given set of characteristic polynomial and minimal polynomial, there are only two kind of non-similar operators, that is two kind of non-similar matrices. Okay, so those are the rational canonical forms. Now the next one, now now we are heading towards the construction of another type of canonical form, which is named as Jordan canonical form. I think the name is totally familiar to all of you, but here I want to show you how does it come from that invariant factor decomposition and that rational canonical form. Okay, so for that I first want to state Chinese remainder theorem for rings. Master degree students actually I think know that Chinese remainder theorem for rings, but this is new for graduation students. So what is we know the actually Chinese remainder theorem in number theory. It is the Chinese remainder theorem version for rings. Those are equivalent. There is no difference between them. So Chinese remainder theorem for rings is, if here we take k number of ideals, and then we then the map R goes to R quotient A1 times R quotient A2 times R quotient AK, defined by the natural way R goes to R plus A1, comma R plus A2, is a ring morphism with the kernel A1 intersection A2 dot dot AK. Okay, and if the ideals are mutually co-maximal, what does co-maximal means? Any two ideals I and j, capital I and capital J, are called co-maximal to each other if I plus j is equal to the total ring R. Okay, here if the ideals A1 to AK are mutually if they are mutually co-maximal, then the above map becomes onto, that is surjective, and the kernel becomes A1 intersection A2 becomes A1 into A2 into AK. Okay, so finally the by the first isomorphism theorem we get R quotient A1 A2 AK, that is R quotient A1 intersection A2 intersection AK is isomorphic to the right hand side R quotient A1 product R quotient A2 dot dot R quotient AK. Okay, now here if we remember the hypothesis of our main theorem, fundamental theorem of invariant factor form, we took our a PID. So here R is a PID, and if I take any non-zero element A from R, as R is PID, so R is UFD also. UFD means unique factorization domain. So any non-zero element can be factorized as prime powers. So R can be written as P1 to the power alpha 1, P2 to the power alpha 2, where Pi's are the distinct primes and U is a unit. Now we can observe that as Pi, Pj are distinct primes, then ideal Pi to the power alpha, ideal generated by Pi to the power alpha I plus ideal generated by Pj to the power alpha j is equal to what? Is equal to ideal, it becomes the ideal generated by GCD of these two factors. That means GCD of Pi and Pj, as Pi and Pj distinct primes, GCD is 1. So sum of these two ideals become GCD, becomes ideal generated by 1. That means it becomes R. So this ideal plus this ideal becomes R. So they are mutually co-maximal. So ideal generated by each power of primes becomes co-maximal. Okay. Then by Chinese remainder theorem, we see that product of each of the ideals becomes intersection of those ideals, and it becomes, and the value becomes what? That value becomes ideal generated by LCM of this factor, this P1, P2, P1 to the power alpha 1, P2 to the power alpha 2, dot dot PS to the power alpha s, and LCM of this becomes the element A itself. So this ideal becomes A itself. So by Chinese remainder theorem, it becomes, the left hand side becomes R quotient A itself, isomorphic to the right hand side R quotient P1 to the power alpha 1, direct sum R quotient P2 to the power alpha 2, dot dot R quotient PS to the power alpha s. And this isomorphism is as rings as well as R modules. Okay. Now, if we apply the above discussion to our fundamental theorem of invariant factor form, so here we can then here in that theorem we can write M is direct sum as free part and torsion part. Free part is R to the power some smaller, and the torsion part was each factor was R quotient some A1, R quotient some A2. Each A1 can be factorized as power of primes. So ultimately the torsion part can be written as R quotient some power of primes P1, direct sum R quotient some power of primes P2, where P1 to the power alpha 1, PS to the power alpha s are positive powers of primes. And we have to here we should note that here the primes are primes may not be distinct. Okay. These prime powers P1 in this theorem, those prime powers P1 to the power alpha 1, P2 to the power alpha 2, PS to the power alpha s are called elementary divisors of M. Okay, those A1, A2 were invariant factors. Here, those prime powers are called elementary divisors of M. Now, I want to actually calculate the Jordan canonical form for a linear operator. For that, I took a finite dimensional vector space over A and a linear operator. And with help of that, we have already obtained rational canonical form and invariant factors. Okay, F1x, F2x, and Fmx. Suppose so. With in the view of our previous discussion, each F1x, each F2x can be expressed as the prime powers of some polynomial. Now, if I take the, it is very important. So here consciously, if we take the field as algebraically closed, then each power, each factor can be factorized, each polynomial can be factorized linearly. That means highest degree of prime is 1 x minus alpha. These are the form of prime factors. So each invariant factors can be factorized in the form of some power of x minus alpha, some power of x minus alpha, beta, like that. So finally, we obtain, as V is a torsion module, so there is no free part. So finally, we obtain that V is isomorphic to fx quotient x minus lambda 1 to the power k1 dx and fx quotient x minus lambda 2 to the power k, ideal generated by this. And you can observe that this lambda 1, this lambda 2, and lambda t, those are actually eigenvalues of t, because the multiplication of invariant factors are was characteristic polynomial of t, and roots of characteristic polynomials are eigenvalues of t, and those factors are actually factors of characteristic polynomials. So roots of those factors become eigenvalues of t. So these lambda 1, this lambda 2, lambda t all become actually eigenvalues of t. Now, for any eigenvalue t, suppose I take any arbitrary, any one direct summand from there. If we take any one eigenvalue lambda, then this becomes a basis of this direct summand. Okay, this observation we have already done that process in obtaining rational canonical form. With help of this basis, we can obtain another basis. The main basis was 1 bar x bar to the power k minus 1. Highest power was x minus lambda to the power k. So highest power in the basis will be x bar to the power k minus 1. So with help of this basis, I obtain another basis. It will be actually the next basis b lambda will be helpful to us in obtaining in this describing Jordan canonical form. This basis is 1 bar x bar minus lambda square, ultimately x bar minus lambda whole to the power k minus 1. Now, so for obtaining the matrix of T, we have to operate. We have to see how does T operate on the basis elements. So how does X act on the elements of B lambda? So the first basis element is 1 bar. So operating X bar on 1 bar, we obtain this. So I am rewriting this in this way, so that I can see that the first column of the matrix will be lambda, second term is 1 because the coefficient is 1, and the remaining coefficients are 0. The second correspondence is x bar minus lambda goes to x bar minus lambda to lambda into this plus this. So the matrix will be 0 into 1 bar plus lambda into this plus 1 into this. So the matrix will be, the second column of the matrix will be 0, lambda, 1, and then all the remaining terms are 0. So in this way, we obtain the matrix of T restricted on the T invariant subspace fx quotient x minus lambda to the power k with respect to the above basis B lambda, which is this. And we see that it is nothing but the Jordan block. It is the K cross K Jordan block for the eigenvalue lambda. And it is that matrix is, I think, is very well known to all of you. Now I want to give the formal definition of Jordan block. Jordan block is nothing but a K cross K matrix with lambda along the main diagonal and 1 along the first sub diagonal, or you can say it is first super diagonal, depicted in the above way. Is called K cross K elementary Jordan matrix with the eigenvalue lambda, or the Jordan block of size K with eigenvalue lambda. So finally, we obtained, it was the matrix was for one direct summand. So finally, as each direct summand are T invariant. So finally, we obtain the final matrix of T, where each block is the Jordan block for the corresponding direct summand. That means the corresponding eigenvalue. Okay, J1, J2, J3. And so this matrix is called the Jordan canonical form for T. So difference between Jordan canonical form and rational canonical form, here each factor is linear factor. Because we took the field is algebraically closed. And two observations are very important here. If a matrix A is similar to a diagonal matrix, then that diagonal matrix is actually the Jordan canonical form of that matrix or for that operator. And any two matrix or any two operators are similar if and only if they have same Jordan canonical form. Okay. Now we take this is the we are actually in the end of my lecture. We took the same example as the rational canonical form one. I just want to show the difference between the Jordan canonical form and the rational canonical form. We take the same characteristic polynomial, same minimal polynomial, and we have that possible invariant factor decompositions. But instead of calculating companion matrix, here I want to calculate the Jordan block for each elementary divisors. Here elementary divisors for the first invariant factor decompositions are those x minus 2, x minus 1 whole square, x minus 2, x minus 1 whole square. We have mentioned that primes may not be distinct in the theorem. And the second, for the second decomposition, the elementary divisors are x minus 1, x minus 2, x minus 1, x minus 2, and x minus 1 whole square. X minus 1 whole square. And here there will be there should be a comma between them. Okay. So for each 1 degree polynomial, Jordan block is nothing but 1 cross 1 matrix consisting of only the eigenvalue 2 or 1. Okay. So here we only higher degree polynomial is x minus 1 whole square, and for x minus 1 whole square, that Jordan block is this. In the diagonal, the eigenvalues are there, and the subdiagonal one is there. So finally, the possible Jordan, the first Jordan canonical form of T is this, and the second Jordan block is this. Okay. Those are my I have used. You can see Damitfoot or Hungerford for those kind of theories. There is a small discussion in those books, and thank you. I'm finished. Okay.
So elaborately presented. The two lectures were too good with so many examples. Mainly the students will be more benefited with the lectures, I think. And we have a few questions from the audience that I will take only one or two of them. One has asked, Subhash Mandal has asked that, is there any connection between module and tensor?
Obviously, I just want to mention, I want to answer this question briefly. There is a huge connection between tensor and module. If we take any two module, suppose we take M as an R module and N as a left R module, take M as right R module and N as a left R module, then we can give a tensor structure M cross N by a quotient module structure. There actually is need a vivid discussion for this tensor. Okay, I want to mention that if we go through the module chapter of Damitfoot, then you will get the tensor module section, and there is a very nice discussion about tensor module. Okay.
Okay, would you like to suggest some books other than Damitfoot or something on this module topic?
Module topic, Damitfoot and Hungerford is the best one, I think. For the easier parts of module, the basic part of module, you can see Malik Moderson Sen book or any other book. I think any other basic algebra book. I think mainly I generally use these three books. Okay. There is a books of Lamb, which is very good also.
Okay, thank you all the invited
I have one question.
delegates.
Yes,
okay.
Yes.
One. Actually, Pavella, you have mentioned about Leavitt path algebra, right?
Yes.
Which was probably came in picture the last decade from 2004-5 like that. So
Yes.
you have just mentioned the name Leavitt path. Could you please
Yes.
tell 1-2 sentences for them?
Actually, Leavitt path, now Leavitt path algebra becomes a vast theory. There is a very good book. I can suggest you a very good book on Leavitt path algebra, which is written by Abrams. Abrams. It's a very good book. This is Leavitt path algebra actually connects R algebra and module theory between the graph theory. It connects these two vast areas of mathematics, and R algebra, actually, for the lack of time, I cannot mention what is R algebra. And the motivating part was, here we have seen that there are modules where R is isomorphic to Rn. In vector space, it is not possible. Okay. So R6 can be, if we take a field F, then Fn can be isomorphic to Fm if n or m unequal, so it is not possible. So this main attribute of module, which is different from vector space, it motivates to generate that theory. And if you want to discuss, I can talk to you later, and I can give you the book. The book is very good.
Okay, thank you, Pavelda and Timir sir. Everyone is asking about the PPTs. If possible, we will definitely send the PPTs with our feedback form. The feedback forms will be sent to your registered email IDs. And thank you, Dr. Subhrakanti Chakraborty, to our HOD, and Dr. Pavel Pal from Bankura University, and Dr. Timir Karmakar from NIT Meghalaya. Thank you. If Shubhra you want to say something, or
Yeah, I want to say something because you see, in the long session, we could continue uninterrupted way because of the support from Ramkrishna Mondal, Professor Ramkrishna Mondal, who has given us the support. So I would like to thank him also from all of our part.
Definitely.
Yes.
Okay, thank you. Here we have to the ending session. Thank you. Take care of yourself, and we are looking for the next webinar. So thank you all.
Thank you.
Thank you.
Thank you.